So welcome to lecture 41 of MCS 471, an introductory course to numerical analysis. So today we will have our first review for the final exam. The final exam that happens very shortly on Friday, 10 December, so please mark that date. So this is also the third review in the course. So we had already 2 reviews. So in preparation for the final exam, if you are short in time, you can focus entirely on what is being said and done in this week. But if you, and I hope that that could be sufficient, but if you have to go back, look back, then 2 reviews for the 2 midterms are also very relevant in helping you to prepare for the final exam. So this lecture consists of 2 parts. I will say something very briefly, or actually the most important part is that you do not miss the final exam. And how it will run, which is particularly important if you have not done the 2 midterm exams. And then in the second part of this lecture, there are 5 representative questions. So the first 4 are probably more representative than the 5th one. The 5th one kind of makes the bridge with the material in the second part. Orthogonality is one of the important themes that runs through this course. All right, then first about the final exam, which runs on Friday, 10 December in the morning, a half hour later than when we usually meet. If you have a conflict, please let me know as soon as possible. Certainly before, if at all possible. If you get sick that day, then of course it might not be possible for you to warn me that in advance. But if at all possible, if you have a conflict, let me know about this. So the final exam runs on Friday, 10 December from in the morning. And what is important is that you have to sign up for the exam, just as with the 2 midterms. You must send me an email before 5 p.m. on Thursday. Otherwise, by default, I will assume that you are fine with a failing grade in this class. So the midterm exams were optional, and also the other activities. But the final exam is an activity that you must do, even if you are already in very good standing. So, as before, the exam must be solved individually. Just copying and pasting materials from elsewhere will not give you much credit. So it is an open book exam. So it's important that you can already locate the relevant materials, but just copying and pasting stuff without adjusting the necessary parameters will give you very, very little credit. The other important things, perhaps I would start to emphasize this. So there is the activity item that you must do. So the must sending of an email, I think that's for you to consciously commit time to this final exam. So you should at least spend a couple of hours studying for the exam. So the exam falls at the end of finals week. I hope you're not exhausted by then. So the other important item is the Jupyter notebook. That has been the standard tool that we have been using throughout the course for the homework, for the midterms, for the computer projects. You must also formulate your answers in a Jupyter notebook. I will email the questions as a PDF and as a Jupyter notebook, and you may use that Jupyter notebook to answer the questions. Solutions outside a Jupyter notebook will not be accepted. So saying I ran out of time and I did it on paper, here you have some pictures of it. I will not accept this simply out of fairness to students who are proficient with the technology and who follow the rules. So you must submit to Gradescope, and you must submit on time. Gradescope allows multiple submissions. It might already be good if you have solved half of the exam to actually start uploading just as a matter of backup, just in case something goes wrong. So this is our third review. In this review, I opted for 5 questions. Unlike previous reviews, where perhaps I might have overwhelmed you a little bit, here I focus on 5 of the most important concepts, and I try to give alternatives. So the exam will consist in multiple versions. That allows me still to cover a wide range of the topics that we have seen. It also allows me to maintain the integrity of the exam, as this is an open book exam. So if you have been collaborating on the projects with a partner, then I will make sure that you and your partner will get different versions of the exam. What is the most important thing here? Please review the homework problems. So if you have the homework problems are actually often prototypes of exam questions. So we have done many homework. If you had troubles even getting started with a homework problem, please ask me. If you have submitted homework and the score was rather disappointing, please also contact me or the grader with some questions for feedback. This is the third review, but there was also a very first review that is also relevant for the topics that we covered today. So please also consider this review, the first review, and also you may look at the version of the first midterm exam. If you took the first midterm exam and there were some questions that went wrong, please make sure that you understand what went wrong. Look at the posted solutions. If you did the first midterm exam and it went well, then great for you, but it may still be good to look at the other versions of the first midterm exam. So some of the most important questions are questions that are common to all 3 midterm exams. So that's also a way to see what is most important. So the most important questions were common, except with some numbers different. And most importantly, if you didn't take the first midterm exam, then it might be even good to practice a 50-minute 10-minute session. So download the questions for one of the versions of the midterm exam and try in all honesty and earnesty to do it within the 50 minutes without looking to the answers. So one benefit for having taken the midterm exams is that you have practiced working under time constraints. So with the projects and the homework, you had a lot of time. It was mainly scheduling time that you had to do. But here, with taking the exam, time might be your biggest problem here. All right, so then let's go to the actual review. We have some representative questions. The questions on this review are more elaborate. So here on floating point numbers, there are 3 questions. So on an exam, you might have only 2 out of the 3. So in a way, this is a good review question because I can cover the notion of machine precision, also the arithmetic, and then also the consequences of this. A question that is lacking here is what is the smallest or what is the largest number that can be represented in this number system? So that could be a 4th question here. So we are working with an approximation, idealization. No, it's not an idealization. So it's a representation of the real numbers. But we can only represent here. So the data in this question is that we have 3 decimal places in the fraction. So it's base 10. So that makes it easier, but also makes it that if you do the arithmetic, do not rely on the system itself. In question 2, I want you to demonstrate that you know the operations. So just typing in 3.21 minus 3.19 in a Jupyter notebook, in an execution cell of a Jupyter notebook, will not give you much credit. So it is actually here still a paper and pencil question. For the first question, you must know how to use the numbers. So there is 3, 10, minus 16, and 16. What is the machine precision in this number system? 10 to the power minus 3. The minus is important. I had people writing 10 to the power plus 3. That, if you reason about this cannot be correct. So here in general, so there is a formula, there is the base, base 10, and there is the 3. So these are the numbers that you have to use. An alternative question is what is the smallest number? What is the largest number that you can represent? For that, the exponents matter then. All right, second part of this question. What is the consequence of having only 3 places in the fraction? Let's do the subtraction. So here in the review, it is a subtraction. On the final exam, it could be an addition as well. Here, the 2 numbers are very much alike in the same magnitude. So that means that the alignment is already done. So look at the other questions that we have covered in the review and on the first midterm exam. Before you do any arithmetical computation, you have to make sure that the exponents, they line up. Here that happened automatically. So one, in a way, this is kind of atypical. So you must represent the numbers first in the system. If here they are given 3 decimal places. If they are given with more decimal places, then you must round. If they are given with fewer decimal places, then you must add zeros to this. So the representation consists of the sign, then the fraction. The first number in the fraction, the first digits has to be non-zero, so that's the normalization. So you see that this normalization happens at the result. So you cannot leave the minus 0.0000 there, the minus 007, you cannot leave it. So, and this happens with the adjusting of the exponent. If you shift to, so if you shift the 7 to the left, then with each shift you decrease the exponent by 1. If you shift to the right, then each time you add the exponent. So that shifting may be necessary in the first step. This is a calculation which bothered us when we did the numerical differentiation. So subtracting numbers of a very similar magnitude leads to a loss of significant places. So we actually started with 3 decimal places. You see, when we have to insert zeros, we actually have lost 2 decimal places. So in a way, this is a meaningful computation. We did it very early on in the course, but it has important consequences when we think about numerical differentiation, for example. All right, so the floating point number system is not really representative for the real number. So in real number arithmetic, we have what is called the associativity. So here, associativity means that we do have an equality for any 3 real numbers. If you add up the first 2 numbers and then add the third number to it, or if you do it, if you start from the back, if you start adding up the last 2 numbers and then add the first number to it, with real numbers it doesn't really matter. Here it actually matters. Something that we, and this is important when we do the summations as well. So this has then consequences for the numerical integration, where we do a lot of summations. So summing numbers in from small sorting numbers first is then a good thing. So sorting, it matters if, for example, the numbers vary widely now in magnitude. So in numerical analysis, it's very bad subtracting numbers that are of equal magnitude. It's equally bad to add numbers of different magnitudes. So we touched on this when we talked about relative error. So losing 3 pennies on $1,000 may not be too bad, but or losing $3 here in terms of $1,000 might not matter much. It matters if you add 3 and 3. So here, with this example, you see if you add 3 to 1,000 plus 3, so 1,000 plus 3 is still 1,000 because you have only 3 decimal places in the fraction. So the first addition doesn't really make a difference. And actually, if you add 1,000 plus 3 plus 3 plus 3 plus 3 plus 3, at some point you would think that you double your number, but that will never happen. So you better add the 3 plus 3 plus 3 plus 3 before you then start adding to the 1,000. So you see that here with this example, because of the rounding, the 3 plus 3 plus 1000 matters, but 1000 plus 3 does not make a difference. Okay, so that was the first question. It's an important, so knowing the consequences of point number arithmetic is very critical. We are interested in also the cost in numerical analysis. How much work do we need to do in order to have a certain accuracy? So this is a question on iterative methods, in particular the golden section search method. And we give a function. So the golden section search method, we've seen it to compute the minimum, but it equally applies to computing the maximum. We're always working over an interval. And the first question we ask when we look into a problem is does the method that we propose here to do apply, yes or not? Here you could say, yes, it applies, otherwise questions 2 and 3 wouldn't. But that's not a good justification. So think about what are the conditions. Every method has some conditions on whether or not they apply on. Then we want to have a certain accuracy. So here 3 decimal places. How much work do we need to do? Here for the work is expressed in the number of function evaluations. So the number of function evaluations is typically our cost estimate. So an alternative to this question is the bisection method. Bisection method can be used for the shooting methods when solving boundary value problems. So the function then is the running of another program. So here we have a nice function, but it could also be an extract function. So one can solve question 2 by using the properties of the golden section search method. You can also solve this question by running the code. So this is a good review question. It shows 3 and 2 are kind of equivalent to each other. So on an exam where you have less time, I would either ask 2 or 3 or leave it up to you. So the justification could also be done with a computation. Sometimes this is good sometimes this is not so good. So if you are in time pressure, then sometimes a good reasoning may save you time compared to a lengthy calculation. Or it could also be the opposite. Okay, what did we assume with the golden section search? Well, we assumed that there is only one unique minimum. Here, the keyword in this answer is unimodel. You could also explain in greater detail without using that word unimodel, is that there is a unique minimum in the interval. This can also be answered by a plot. If you can plot it, then you can see that there's only one minimum. Okay, how many function evaluations do we need in order to obtain an accuracy of 3 decimal places? So with this 3 decimal places, well, how many decimal places do we have now? Well, the length of the interval is 1, and if we didn't know any better, you just take the middle of the interval. So the accuracy is 1/2 or 0.5. You kind of know almost the first decimal place. What do we know about the golden section search method is that in each step the interval is reduced with the factor of 0.6. So you know how many steps you need to do by multiplying the 0.5 with this reduction factor. So you can solve this analytically by solving this nonlinear equation here, which can be computed by a logarithm. So this n is a number of steps. We see that we need about 12, 12.9. You could round off here 13. Here I chopped the 12, so 12 steps, but we actually do, well, actually we do 13 steps. But in the first step, we did 2 function evaluations. So that's why we have 13 plus 1 function evaluations. So in your answer, I underlined the equation, but the information, the other information that you need is how many function evaluations you do per step, and then what is the reduction factor. An equivalent, so this is on root finding, this is on optimization, but we have seen the bisection method where the same question would apply. And we've also have seen the fixed point iterations. We also have seen Newton's method. In Newton's method, you have to assume, you have to apply the quadratic convergence. So this is linear convergence. Linear convergence means that you need a constant number of iterations for every decimal step. Or it could also be that that constant number is a fraction. Then what this means is that in every step you gain a constant number of decimal places. Here we run the program, and what is important here is that you have to know what are the critical parameters. And we always read our numbers from right to left. Our numbers are by standard always in floating in scientific notation. What I was about to say here is that I made that comment also at the very beginning. So just copying and pasting code and running it without any modification of the parameters will often not give you much credit. Here for this run, it's important that you make sure that the length of the interval is indeed 10 to the power minus 3 times 5, so that you have the correct accuracy. So for that, we had the function tolerance to take into account flat functions or functions that are rather steep. So if you do the run, so questions 2 and 3 are equivalent, but if you do runs, make sure that you read the documentation for the parameters. So the numerical parameters often have default values, but the defaults are for the examples that were used to demonstrate the functions. In the questions, the difficulty is often that you have to know which parameters to adjust and how to interpret the output. So you can always look at, here we looked at the length of the interval, but you could also compare the number of decimal places. So an alternative question would be to give numerical output and then ask what is the accuracy. And here you see that it was important to change the tolerance on the residual, because you see the two function values are the same, but the points are different. So the locations x1 and which do have different values if we print with 5 decimal places. Okay, 2 questions solved. We're making progress. Conditioning. In numerical analysis, we study numerically stable algorithms for well-conditioned problems. So it is important, just as the previous exercise, that we know what are the conditions on which the method applies. There's also another condition, which is a numerical condition. So numerical conditioning measures the sensitivity of the output to changes in the input. And that is regardless of what method you are using. If the input, if the output is very sensitive to changes to the input, or alternatively, if you make a very tiny change to an input and that gives you huge change in the output, then the problem is ill-conditioned. So linear system solving. So this is the central question in this review. It's also actually the central part in numerical linear algebra, so linear system solving, but also plays a very important role in numerical analysis. So if the condition number of a matrix is like here, 10 to the power 24, and you work with 64 decimal places, so the 64 is your working precision, you may hope to have 64 decimal places accurate, but that can differ if you work with a condition number that is that high. So there are 2 parts in this question. First, what is your estimate on the correctness of any answer that you may hope for in a numerical solver? It doesn't matter what solver that is used here, whether you use LU factorization, QR factorization, or a single value decomposition. How many decimal places can you hope that are correct? That's a very simple computation. That will give you some credit, but the justification is also here very important. The answer is 40. And that will already give you credit. So if you are in time pressure, then look at all the questions. So this is a question that is very important. It was common to all the midterm exams. Here the justification is given in a very elaborate form in the inequality. What is important is that you multiply the condition number here, so this is the 10 to the power 24, with the machine precision. So 64 decimal places means that your machine precision is 10 to the power minus 64. So the right side of this inequality gives you the upper bound on the relative error. So this is how you get to the 10 to the power 24 times 10 to the power minus 64. So in a way, better written is that the justification is minus 64 plus 24. So in a way, this is the calculation that is done when you evaluate the right-hand side. So the 40 is the exponent. So you will actually, if you do this, the reason why it's not written like this is that you have negative 40. So the negative 40 is the exponent that you have. And So negative 40 would be a bad answer. So the negative 40 is for the 10 to the power minus 40. So that is the left-hand side here. Okay, we have seen condition numbers for all our problems. But for linear algebra, this is where it matters most. So the next problem is interpolation. So interpolation also have a condition number. So in particular, we always assumed that the interpolation points were distinct from each other. The most obvious choice is to take them like here in an equidistant way, but the best possible way was to take your interpolation points as the roots of the Chebyshev polynomials. So here, so this question is a question that is asking about the uniqueness of the interpolation problem, and also about a very particular way to compute the interpolating polynomial. But there is a strong connection with linear algebra. We are solving a structured linear system. So a linear system where the coefficient matrix has a particular structure, and because of that particular structure, we can solve this problem in a time, in a cost that is proportional, that is quadratic to the proportional to the square of the dimension, the square of the number of points here. Okay, so this is making a link between the previous question and this question. So the beauty of the course is that you could, and that's also in central, the effectivity, the power of mathematics, is that you start to see the connections between the problems. For sake of preparing for the final exam, make sure that you understand these particular questions. So what is a table of divided differences? And so it's a table of numbers, a triangular table, but what do the numbers mean? So we've seen, so this is not a programming course. This code that is posted for doing Newton interpolation. And by the way, here I present the answers in slides. Another excellent way to prepare for the final exam would be to make a Jupyter notebook of the 5 problems in this lecture here. So in essence, in preparing for this midterm exam, for this final exam, as I'm rambling along, you could, during this time, work with the Jupyter notebook. Reading the questions. So we have a quadratic polynomial, and you see an interpolation problem has 2 data sets. We have points where we evaluate, and we have function values. Here the function values are given by evaluating polynomial. Now, I'm being very explicit now, but Julia is quite good. So a function definition in Julia is writing px like you have at the left-hand side, and then you have to add the stars to it. So you can almost, so the multiplications are omitted here, and also the exponentiation. But the first thing that you will do in answering this question is to find the function p, because this is what you need for the function values. For this particular question here, so interpolation, interpolating a polynomial is good for a benchmark problem. So we know what we are going to obtain. So that's the part of the second question. So what we are computing is the Newton form of this polynomial here. Here is the numerical answer. So we have the table of divided differences. So the first part of the table consists, so the first column consists of the interpolation points, so 0, 1, 2, 3. And then we have the function values. So now here the 3 is the 3 from evaluating the polynomial at 0. What we care for, and let me now write that down in another color, what we care for are the numbers on the diagonal. Why do we care for that? Because these are the coefficients of the interpolating polynomial. The Newton form is, by the way, also known as a discrete Taylor expansion. So with the Taylor expansion, you compute all the derivatives. The divided differences are, in essence, approximations for the derivatives. Here, of course, they are extremely crude because the points are very far from each other. But so this is kind of making the link with the second half of the course, where we considered numerical differentiation. Taylor is also important, was important during the entire course. Now, in answering this question, what is the last coefficient 0? So why is that? Well, here you see the here you see the Newton form. So the answers are quite elaborate, but what you need to write down is the Newton form of the interpolating polynomial. So you see the coefficients. So the 0 comes over here. Then we have the 2, the -3, and the 3. Why is the 3 there? Well, the 3 is there because at 0, when x equals 0, we have the constant 3. And suppose that this 0 now would not be 0. So let me now change again into red. So what if this one would not be 0? Well, observe then that you would have a polynomial of degree 3. The interpolating polynomial is unique polynomial, so there is only one answer. And we started with a polynomial. So the given polynomial also interpolates by construction. So if we would have had a higher degree polynomial, then that would have violated the property that the interpolation question has a unique answer. Unique if all the interpolation points are different. Okay. We're making good progress. One last question. So this question is on orthogonality. So we have covered orthogonality the first time when we encountered this, when we were solving linear systems, and in particular when we were doing data fitting. Know that with the data fitting problem, we have an overdetermined system, and then we don't have a residual anymore. Residual in the classical sense, the b minus a times x, where x is our approximate solution, b is the right-hand side, a is the coefficient matrix. But we do have the important property that that residual vector is orthogonal to the columns of our coefficient matrix. We can solve linear systems with orthogonalization if we modify the Gram-Schmidt method, but we can also use the householder QR. This review question is interesting for the review because it makes the connection with orthogonal polynomials. Orthogonal polynomials that we used for the Gauss quadrature. And in particular, we will have seen Gauss-Legendre quadrature. If you would, so there we started from the Legendre polynomials, we defined them from a three terms recursion. However, if you would not know about the three terms recursion, but if you would know the Gram-Schmidt orthogonalization method, then you can construct an orthogonal basis. And in particular, we will construct an orthonormal basis for the polynomials with the standard inner product. So orthogonality is defined whenever there is a well-defined inner product. And the inner products that we have defined are with integrals. We can fit data points. So remember this exercise from Moore's law, the number of transistors on a chip. This roughly still doubled every year or every other year. So we can also fit functions. We can, instead of interpolating, we can represent a function as a linear combination of orthogonal polynomials. And the coefficients in that fitting are obtained by the integrals. So that is the relevance for this exercise here. It's a good review exercise because it allows you to see the connections between, say, the orthogonal polynomials we encountered with Gaussian quadrature and the orthogonality that we have seen in the data fitting. It is a symbolic method. So in doing the calculations, they are integrals of polynomials. This is a paper and pencil exercise as it is represented here, but you can use, and if you do the preparation via a Jupyter notebook, you can redo all the computations with SymPy. So we normalize our basis. So we, instead of 1, we have 1 over the square root of 2, because that gives us then that 1 has 1 over square root of 2 has length 1. So this is also then the 2 is the 2 norm, is the norm squared of 1. How do we then apply the Gram-Schmidt? So we make the inner product of the new function with all the previous elements in the basis. So here we have only one element in the basis, P0. We make the inner product of the new, and we subtract the part from it. So here you see how we get to this. So with P1, we subtract from it the part that is not, that is in the part that comes from the representation in the basis, and then we normalize. And this is done here too in the second step for x squared. So I'm running out of time now. So I'm leaving this question rather open as making the transition to the next part, the next review that will happen in the following lecture.